operating systems on that same computer. For example, you might have a computer like I do that runs Mac OS, and you can run Windows 11 and Linux all at the same time on that same system. This means that you have a separate operating system, a separate CPU, dedicated memory, and a separate network connection for each of these virtualized operating systems. If all of these different operating systems are virtualized on your desktop, then we refer to this as a host-based virtualization. This means you're running something like Mac OS as the primary operating system, and then virtualizing other operating systems on top of that. In an enterprise environment, we tend to use a single computer that has multiple operating systems running on it in a virtualized form. In virtualizing all of these different systems, this means that you have a separate operating system, a separate CPU, dedicated memory, and a separate network connection for each of these virtualized operating systems. If all of these different operating systems are virtualized on your desktop, then we refer to this as a host-based virtualization. This means you're running something like Mac OS as the primary operating system, and then virtualizing other operating systems on top of that. In an enterprise environment, we tend to use a single computer that has multiple operating systems running on it in a virtualized form. There is no desktop to choose from. Instead, you have a single device that has multiple VMs running on that single computer. And although virtualization has become very popular on our computers and our servers, this is a technology that we've been running since 1967 when it was first introduced on IBM mainframes. We're using that same concept that we used back then to virtualize our modern operating systems on modern hardware. There are a lot of things you can do with a virtualized operating system, or what we commonly refer to as a virtual machine, or VM. For example, if you're building your own applications, you might want to create a virtual machine that handles sandboxing. Sandboxing is an isolated environment that you can use during the development process to try out different aspects of code or to run things in a different OS to see what the effect might be. The benefit here, of course, is that you're running this in a virtualized environment that is designed for testing. So if something doesn't work properly, or it even creates a problem with the operating system, the only thing that's affected is that single virtual machine. And because most of these virtualized systems have ways to take snapshots of the configuration at any point in time, you can create a snapshot, make some changes to that virtual machine, and if those changes cause a problem, you can revert back to the previous snapshot in a matter of moments. This also means we can create multiple virtual machines running multiple operating systems and be able to run that code in each one of those VMs to see what the effect might be. This means developers can write their own code, put them into a virtual machine in a protected and secure environment that won't affect anything if something happens to go wrong. And once the entire application has been written, they can put that code onto a test virtual machine that mirrors an actual configuration that runs in production. This means the developer can now run their test code in an environment that is very similar to what the end users will be using. Sometimes virtualization is not about application development, but instead being able to support operating systems that we don't normally use. For example, you may be running Windows 11 on your desktop, but you might have some applications that only run in Windows 10. One way that you can run both your Windows 11 desktop and the Windows 10 apps at the same time is through the use of virtualization. That's exactly what we've done here. I have a Windows 11 system that I'm running in one window and a Windows 10 system that I'm running in another. This allows me to switch back and forth between operating systems and run applications that may only run in one particular OS. This means I can switch back and forth between different operating systems and run the application that works best in that particular version of the OS. Here's a better view of this. You can see that we are running simultaneously on this computer a Windows 11 Pro system and a Windows 10 Pro system, both at the same time, and I can switch back and forth between either of these at any time without having to reboot my system. And of course, this doesn't have to be all the same type of operating system. We could have cross-platform virtualization like the one you see here. So you might run Mac OS on your desktop, run a Windows VM, run a Linux VM, and run other types of operating systems all on that same platform. You can also do this on demand. So if you need to run one particular application in the afternoon that only runs in Windows 11, you can start your Windows 11 virtual machine, run your application, and then shut it down. You have complete control over which application you're running in which operating system, and you don't have to reboot just to be able to change the OS that you're using. This is obviously saving time because we don't have to reboot or find another system just to run the application we need. And we're also saving resources because we're able to run all of these different operating systems on one physical computer. Here's a better view of this multi-platform use of virtualization. I'm running this on my Mac OS desktop, and I'm running a native version of the Mac OS browser on the left side. On your desktop, run a Windows VM, run a Linux VM, and run other types of operating systems all on that same platform. You can also do this on demand. So if you need to run one particular application in the afternoon that only runs in Windows 11, you can start your Windows 11 virtual machine, run your application, and then shut it down. You have complete control over which application you're running in which operating system, and you don't have to reboot just to be able to change the OS that you're using. This is obviously saving time because we don't have to reboot or find another system just to run the application we need. And we're also saving resources because we're able to run all of these different operating systems on one physical computer. Here's a better view of this multi-platform use of virtualization. I'm running this on my Mac OS desktop, and I'm running a native version of the Mac OS browser on the left side. On the right side, I'm running a Windows instance and Windows applications inside of that window. And here in the middle is a window that's running Linux, and I'm running Linux applications in that window. I'm able to move back and forth between any of these at any time. I'm able to start and stop different operating systems and use whatever application I happen to need at that time, regardless of what operating system it uses.
Think test optional means test scores don't matter? Think again. Most top colleges are bringing back test requirements, and submitting scores can triple your students' chances of getting in. At Yale, applicants who submitted scores had a 6% admit rate. Those who didn't, just 2%. So yes.
To be able to take advantage of virtualization, you need something that is going to manage the process of keeping all of these different systems running. This is the virtual machine manager, often referred to as the hypervisor. The hypervisor is the software that manages this entire interaction between the virtual world and the physical system it's running on. Hypervisors can run on almost any system, but many modern hypervisors can take advantage of CPUs that have specifically been built with virtualization in mind. And once this hypervisor is running, it can allocate CPU cycles, memory, networking information, and keep all of that separated between all of the different virtual machines. To understand more about how all of these different operating systems interact with the hypervisor, I've created this block diagram that starts at the very bottom with the hardware. This is the physical system that the hypervisor is running on. On top of that hardware is the hypervisor, and above the hypervisor are all of the different virtual machines. You'll notice that each virtual machine has its own guest operating system and applications running within that OS. Since each one of these virtual machines has its own guest operating system installed and running, there is a significant amount of overhead that takes place every time you start a new VM. This means you'll need enough CPU cycles, enough memory, enough drive space for all of these VMs to operate simultaneously on the same physical piece of hardware. This type of hypervisor that sits right on top of the hardware is known as a Type 1 hypervisor. You might also hear this referred to as a bare metal hypervisor. That's because there's no operating system down at the lowest level. The hypervisor effectively is the primary operating system that is running on top of this hardware. Examples of a Type 1 hypervisor would be VMware's ESXi or Microsoft's Hyper-V. If you're running a hypervisor on your own desktop, then you're running a Type 2 hypervisor or a hosted hypervisor. This means you would have the hardware that you're currently using for your computer. You have the normal operating system that you're using. You might be running Windows as the primary operating system on your computer. I'm running Mac OS X on my computer, and that operating system is where you would use all of your native applications. On top of that operating system, we would then run some hypervisor software. On your system, you might be running VMware Workstation, Oracle VirtualBox, or Parallels Desktop to be able to provide that hypervisor running on top of your current operating system. At that point, the Type 1 hypervisor VMs and the Type 2 hypervisor VMs are exactly the same. The only difference is how you're running those VMs. With Type 1, it's running on bare metal, and on Type 2, it's running on a hosted operating system. We mentioned earlier that some CPUs have been specifically constructed to work in a virtualized environment. If you're running an Intel processor with this support, they refer to this as virtualization technology, or VT. If you're running an AMD processor, the same type of functionality is called AMD-V. The hypervisor is allocating memory to each of these virtual machines, and it's using parts of your physical memory inside of your system. So you have to make sure that you have enough RAM in your computer to be able to support all of these different virtual machines running simultaneously. And of course, each of those virtual machines contains a complete installed operating system, the applications that run in that operating system, and the data that you store in those applications. That means you'll need enough drive space to be able to support a fully built operating system and all of the necessary applications in each one of those VMs. And from the networking perspective, you have complete control over how that virtual machine is able to interact with other devices in the outside world. Most of the hypervisors that you'll run on your local computer, the client-side virtual machine managers, have their own virtual networks that are configured internally to your system. This means the hypervisor will be in control of determining whether that VM can only communicate to itself or if it can communicate outside of that VM to other devices. Some hypervisors will configure a shared network address. This means that the hypervisor has its own IP subnet that's different than any other network that you're currently using. And when devices on that network need to communicate out to the physical network, it performs a network address translation to be able to communicate outside the scope of that hypervisor. You can also configure a virtual machine to look and act as if it's any other device that's on your local network. We refer to this as a bridge network address. There's no network address translation, and all of your virtual machines have the same IP subnet and act as if they are on your same local network. And if this is a highly secure virtual machine that should not be communicating to any other devices, you can configure your hypervisor with a private address so that virtual machine can only communicate with itself and any other devices that you decide. Security is always a concern when you're running so many different operating systems on one physical device. Fortunately, there have not been any significant security breaches relating to hypervisors, but this is something that hypervisor manufacturers and developers are always aware of. One type of security vulnerability that is top of mind for these hypervisor developers is a VM escape. This is when malware might find itself onto one virtual machine and use a flaw in the hypervisor to be able to communicate to other virtual machines that are supported by that same hypervisor. This would obviously be a significant issue if someone was able to do this. This would allow malware that would normally be isolated on one single virtual use a flaw in the hypervisor to be able to communicate to other virtual machines that are hypervisor manufacturers and developers are always aware of. One type of security vulnerability that is top of mind for these hypervisor developers is a VM escape. This is when malware might find itself onto one virtual machine and use a flaw in the hypervisor to be able to communicate to other virtual machines that are supported by that same hypervisor. This would obviously be a significant issue if someone was able to do this. This would allow malware that would normally be isolated on one single virtual machine to be able to reach out and control or access data that might be on a different virtual machine. This would obviously be a significant security concern, and thankfully, we've not seen any significant breaches that are related to a VM escape. Of course, each of these virtual machines is its own self-contained operating system, and we have to be sure that we configure the security for that virtual machine as if it was a standalone workstation or standalone server. This means we would use traditional security controls on those devices. We would configure a firewall, we would install the appropriate anti-malware software, and configure the operating system to be hardened just like any other OS. One technique that some attackers like to use is to publish a virtual machine on the internet for anyone to be able to download and use. But of course, these malware authors are embedding their malware inside of that VM, and when you start running that virtual machine on your own environment, you're running an operating system that is already infected with the malware. This is why it's always a good idea to build your own virtual machine so you know exactly what software is running in those devices. And if you are downloading a virtual machine from the internet, make sure that you are completely aware of the information that is contained on that VM and that you're taking the appropriate security mechanisms to keep that VM and all of your data safe. Well, if we can run a separate operating system in a window on our desktop, why can't we virtualize the entire desktop? That is a technology known as Virtual Desktop Infrastructure, or VDI. This means that your desktop would run as a virtual machine on a separate device, commonly across the network or in the cloud, and the only thing that you would really need on your desk is a keyboard, a mouse, and some type of display. Sometimes you may hear this referred to as Desktop as a Service, or DaaS. This means you don't need a significant CPU, a lot of memory, or even a lot of storage on your local computer. All of the work is done on the virtualized client that's running on that virtual system. Obviously, we are sending information to update the screen that is running on our local device, so we obviously need some type of network communication, but these days we tend to have significant bandwidths available to us, which allow us to run technologies such as virtual desktop infrastructure. Once you're running the virtual desktop, it looks, acts, and interacts with you exactly like a normal OS. From the user's perspective, they're running an operating system that's running technology such as virtual desktop. Perspective, they're running an operating system that's running on their local device, even though they're really running this OS as a virtualized system across the cloud. We mentioned earlier that virtual machines need their own operating system installed on each individual VM, and that adds some significant overhead to the entire virtualization process. But what if you could remove that operating system component and only virtualize the applications? That's the idea behind application containerization, where you have separate containers that are built for every application that you'd like to run on that operating system. Just like a virtual machine, each one of these apps is self-contained. It has no idea that other application containers happen to be running on that same physical system, and none of those containers are able to interact with each other unless you configure that in the containerization software. And since there is no operating system, the entire container image is much smaller than the traditional virtual machine. This makes this very lightweight. You're able to transfer them very quickly from one place to the other, and they're very portable, which means you can move them from one physical device to another without making any changes to the application container. So here's a side-by-side view of a traditional virtualized application configuration and a containerized application configuration. You can see in the virtualized applications that each one of the VMs has their own guest operating system, but the containerized applications have a single host operating system. This certainly simplifies the process of managing the operating system since there's only one OS that you'll need to patch, update, and maintain. On top of the host operating system, you would run containerization software. One of the most popular is Docker. And then on top of Docker, you would have the individual Docker containerized applications. One significant difference in containerized applications is they're relying on that host operating system, which generally means that each one of these applications must be configured to run on that host OS. You generally would not be able to run a Windows container, a Linux container, and a Mac OS container all on the same version of Docker. Of course, if you were running VMs, you could have different guest operating systems on each of those, but of course your trade-off is the overhead that you have with a virtualized application. You'll often hear cloud computing described as a server that's simply hosted somewhere else. But in reality, cloud computing provides extensive functionality, and we'll talk about some of those advantages in this video today. It certainly allows us to take the applications and services that normally we would host in our own data center and host those services anywhere we'd like in the world. One interesting characteristic of cloud computing is that these services are located at many public cloud service providers, which means we have effectively as much CPU, drive space, and network as we could possibly want to use. Another powerful characteristic of cloud computing is that you can deploy an entire application instance anywhere you'd like at any time by simply pressing a button. This is very different than the old days of physical data centers where you had to purchase a server, wait for that purchase to arrive, unbox the server, put it into a rack, turn it on, install the operating system and the application, and finally connect it to a network just to be able to use that app. With cloud computing, all of this is done in a matter of moments, and you can deploy as much or as little of this as you need. And of course, as the demand for that app tends to decrease over time, you can remove those resources from the cloud at any moment. Many of these public clouds are located in key geographical areas around the world. That means that you can deploy your app to where it makes the most sense. If more people would use this app in Europe, then you may want to use a Europe-based cloud service provider. If more of your customers are in the United States, you may want to have some US-based cloud services there. The cloud is also about efficiency. If you only have a particular application that you need during particular times of the year, you can simply spin up those application instances, use that application, and when you're done, you can turn off those particular instances. This means that you now have more financial control over how this application is deployed, and you don't have to put up a lot of money up front just to buy all of this infrastructure. Instead, you simply pay over time by using the cloud. When most people think about the cloud, they probably think about a public cloud. These would be the cloud infrastructures provided by Microsoft, Amazon, Rackspace, and many other cloud providers. We call these public clouds because you're able to access these clouds publicly from anywhere you happen to be on the internet. A private cloud is a cloud infrastructure that you are running in your own private data center. You would need to purchase all of the equipment and storage required to build that cloud, but once that's in place in your own infrastructure, you can deploy new applications, use the capabilities of these cloud-based infrastructures, but keep all of that information within your control in your private data center. Many organizations use a combination of both of these. They might have a private cloud that they're running their own internal and private apps on, and they might also have a public cloud that they use for deployment and access by other folks on the internet. Both of these are very common implementations, and in many organizations, you will see both of these used simultaneously. The idea of purchasing your own cloud and deploying it in your own data center requires a bit of a cash outlay. So some organizations will partner with other organizations that provide a similar set of services and build their own cloud that they can share amongst all of them. This means that these smaller organizations can still take advantage of the technologies that cloud provides, but it doesn't require that enormous cash outlay to begin with. Not every cloud implementation is designed in exactly the same way. There are a number of different implementation models that you might find. One of these is Infrastructure as a Service, or IaaS. You might also see this referred to as Hardware as a Service, or HaaS. You can think of this as renting time on a piece of hardware that's somewhere in a cloud infrastructure.
First, we offer overnight boarding. Your pet will stay overnight in your sitter's home and not only be treated like part of the family.
This means that the cloud provider can provide you with a CPU and storage space, but you would still be responsible for installing operating systems, maintaining the operating system and keeping it up to date. And this is Infrastructure as a Service, or IaaS. You might also see this referred to as Hardware as a Service, or HaaS. You can think of this as renting time on a piece of hardware that's somewhere in a cloud infrastructure. So some organizations will partner with other organizations that provide a similar set of services the same way. There are a number of different implementation models that you might find. One of these is Infrastructure as a Service, or IaaS. You might also see this referred to as Hardware as a Service, or HaaS. You can think of this as renting time on a piece of hardware that's somewhere in a cloud infrastructure. This means that the cloud provider can provide you with a CPU and storage space, but you would still be responsible for installing operating systems, maintaining the operating system and keeping it up to date, and maintaining the security of the application. The cloud provider certainly has access to the hardware that you're using, but all of that data that you're storing would be within your control and your control only. This gives you some additional security over other types of cloud deployment models, but it also requires a lot more work to be able to manage and maintain this system. One common use of an infrastructure as a service deployment would be with something like a web service provider. For example, if you're on ProfessorMesser.com right now, you're using a cloud-based server that was deployed in an infrastructure as a service model. I simply rent time on those systems, but I'm responsible for maintaining the operating system, the applications, and the data. Infrastructure as a service has a significant management overhead associated with it. On the other side of the spectrum would be software as a service, or SaaS. Software as a service is on-demand software. You simply use your username and password, you log into a system, usually with a web-based front end, and you're able to take advantage of that particular application. You don't have to do any type of management of the application. There's no operating system updates. You don't have to manage any software applications or code, and you don't even have to worry about where the data happens to be. All of these requirements are managed by the cloud service provider through the software as a service deployment model. This also means you don't need a big development team to be able to write any applications because the application has already been written for you with software as a service. You would simply log in and use that application, and if there's any updates that need to be made to that application, they are made by the application provider themselves. A good example of a software as a service would be things like Google Mail or Microsoft 365, where you don't have to build the Google Mail infrastructure. You simply use your username and password, and you're able to send and receive emails. A deployment model that's in the middle ground between infrastructure as a service and software as a service is one we refer to as platform as a service, or PaaS. Platform as a service doesn't require you to maintain any operating systems, and you don't have to have your own data center, but you do have to work on building the application that will run on this particular platform. This is an interesting hybrid between the software as a service model and the infrastructure as a service model because you still have to write the application, but the platform that you're using to write and to run the software is all operating on the platform used by the platform as a service provider. You can think of piecing together different modules of an application in the same way that you might piece together different types of building blocks. You determine how these building blocks are arranged and ultimately what these building blocks will provide for you. But it's your responsibility to put all of these blocks together in a way that makes sense for you, and only you will have access to this application because you built it as part of this platform as a service infrastructure. There are many different platform as a service providers that you could choose from on the internet. One of the more popular PaaS providers is from Salesforce.com. Many people know Salesforce as a software as a service provider where you simply log in and use their platform. But they also have an extensive development platform that you're able to build your own application to work exactly the way you'd like. And that particular arm of Salesforce.com operates as platform as a service. Many public cloud providers will provide you with a responsibility matrix so that you know exactly what parts of this service are managed by the cloud provider and what parts of this service are the responsibility of you, the customer. For example, if you're building out your own cloud services or doing everything on your own premises, effectively everything is your responsibility. You would need to be responsible for the data, the infrastructure, the applications that you're building, the network connectivity, the operating systems themselves, and the physical platform itself. Software as a service is one where the provider is managing a very large amount of that infrastructure, all the way from the physical data center up through the application itself. You as the customer may want to provide some additional identity and directory infrastructure for authentication. You might want to have your own accounts configured within the software as a service platform, and you'll provide a responsibility of you, the customer. For example, if you're building out your own cloud services or doing everything on your own premises, effectively everything is your responsibility. You would need to be responsible for the data, the infrastructure, the applications that you're building, the network connectivity, the operating systems themselves, and the physical platform itself. Software as a service is one where the provider is managing a very large amount of that infrastructure, all the way from the physical data center up through the application itself. You as the customer may want to provide some additional identity and directory platform. With Platform as a Service, you as the customer will be responsible for writing your own applications. The PaaS provider will provide you with the platform, and you, the customer, will begin writing the applications that will run on this platform. And with Infrastructure as a Service, the provider commonly provides the data center, the network connectivity, and the hardware for the CPU and the storage. You as the customer might have the option for installing your own operating system, and as the customer, you will be responsible for everything else that is being used on that cloud deployment option.
Hold on. Before you pay for yet another app to manage your team, let me introduce you to Connect Team, the one platform that replaces all of these.
Many organizations will build their own private cloud. They have their own data center that they manage themselves. They will purchase their own equipment and their own storage, and they will install and maintain everything themselves. Sometimes you'll see this referred to as an internal cloud or a private cloud. All of those resources in their private cloud are dedicated for their use only. No one else will be using any of the resources that they have acquired and that they maintain in their own internal cloud infrastructure. There's obviously a significant cash outlay to be able to purchase all of this equipment initially and install it into your data center. But once everything's in place, you no longer have those pay-as-you-go or metered costs associated with a cloud infrastructure. You can use as much of your private cloud as you would like, and there's no additional cloud costs associated with that. Some organizations prefer not owning any equipment or maintaining any data center, and instead will use a cloud that was created by others. In this case, it would be an external cloud, or what we often refer to as a public cloud. So if you are using public cloud services on Amazon, on Rackspace, on Microsoft, then all of those cloud services would be considered a public cloud. There are many other customers that are deploying their own cloud-based services, so both you and those other customers are all sharing the same resources to be able to deploy all of those cloud-based technologies. Obviously, in these public clouds, one customer is not able to see any data from another customer, but all of you could be using the same storage drives, the same CPUs, and the same network as every other customer in that public cloud. And although you didn't have to pay for any additional costs up front to put together this cloud, you still have to pay for the resources that you're using. Some cloud providers charge you a fixed rate per month, or they might charge as you go in more of a metered pricing. So your organization will need to determine if a private cloud might be something worth investing in, or if a public cloud might be a better option. For many organizations, costs are certainly an important consideration. And with cloud services, you could be billed differently depending on the cloud provider and the service that you're using. You may find that some of your cloud services are billed back to you or a private cloud. All of those resources so all of the other network as every other customer in that public cloud. And although you didn't have to pay for any additional costs up front to put together this cloud, you still have to pay for the resources that you're using. Some cloud providers charge you a fixed rate per month, or they might charge as you go in more of a metered pricing. So your organization will need to determine if a private cloud might be something worth investing in, or if a public cloud might be a better option. For many organizations, costs are certainly an important consideration. And with cloud services, you could be billed differently depending on the cloud provider and the service that you're using. You may find that some of your cloud services are billed back to you using metered utilization. This means that you as the customer are paying for how much of these resources you are using. So if you're paying to have traffic uploaded to you inside of this cloud, all of that traffic would be ingress traffic, and there may be a cost associated with every byte that you would transfer of that ingress traffic. There's probably also a cost to store the data on the storage drives of that cloud-based service. And if customers are downloading information from your cloud services, then you are sending that information to the user, and all of that information would be priced on the egress traffic costs. And if customers are downloading information from your cloud services, then you are sending all of that traffic out, or it would be egress traffic, and there might be a different cost for egress traffic versus ingress traffic. At the end of the month, all of these costs are added up, and they provide you with an invoice of what you would need to pay for that month. If you have a very busy month, then you probably are paying more than if it's a slower month because it is a metered utilization or based on how much you're using. On the consumer side, we tend to see a lot of cloud-based services priced on a non-metered basis. This means that it is a fixed price for a certain amount of resources, and those services generally charge you based on the maximum amount of storage that you could use. For example, you might pay a certain amount for 2 gigabytes of storage in the cloud. And no matter how much you upload or how much you download, you're always paying the same amount every month for that maximum block of storage. One of the most useful characteristics of cloud computing is the ability to scale up or scale down at any time. This means as customers or applications become more active, you can scale up your infrastructure to be able to handle that load. And perhaps at different times of the year, when things get a little bit slower, you can scale down your infrastructure so you're only paying for what you need. And of course, you're able to make these changes at any time and very often automatically. So it would not be unusual for you to push a button and instantly deploy a new application instance to be able to handle the additional load. We refer to this ability to instantly scale up or scale down based on the load as elasticity. Another very appealing characteristic of cloud technologies is that it always seems to be available. This ability to maintain uptime and availability is an important characteristic for any infrastructure, but with cloud-based technologies, there are many redundancies in place across many different data centers. This means if one data center is having problems with a particular drive array or with a network connection, that other parts of that infrastructure can pick up the load. And in very extreme cases, some of these cloud providers will have completely separate data centers, and they can move everyone from one data center to the other to maintain that uptime. The cloud also allows us to appear to be everywhere all at once. This means that we can have a database that we're maintaining here in North America and be able to have that information automatically duplicated to other data centers around the world. Sometimes this file synchronization is something built into the application and is maintained by the customer. But some cloud infrastructures will automatically synchronize this data behind the scenes, especially if they need to move you from one data center to another. And to be able to get the best efficiency for the infrastructure that's been installed in these cloud-based data centers, we need to have many customers using all of this equipment all the time. We refer to this characteristic as multi-tenancy. That means there are many different tenants effectively living in that cloud infrastructure, and they are all working and operating simultaneously across all of those resources. There are obviously technologies, processes, and procedures in place to maintain separation between all of these different customers. But by having all of these customers use all of these cloud-based services simultaneously, the cloud provider can provide an efficiency in technology and an efficiency in cost. This data behind the scenes, especially if they need to move you from one data center to another. And to be able to get the best efficiency for the infrastructure that's been installed in these cloud-based data centers, we need to have many customers using all of this equipment all the time. We refer to this characteristic as multi-tenancy. That means there are many different tenants effectively living in that cloud infrastructure, and they are all working and operating simultaneously across all of those resources. There are obviously technologies, processes, and procedures in place to maintain separation between all of these different customers. But by having all of these customers use all of these cloud-based services simultaneously, the cloud provider can provide an efficiency in technology and an efficiency in cost.